All right, welcome back to statistics. So today we're going to finish covering section 3.2. This is measures of spread. Okay. Now I'm going to do this a little bit out of order. So we're going to take a little bit of section 3.3, excuse me, before we tackle this. All right. So the idea that I want to introduce you to is something called a z-score. Okay. Now we're going to do a lot of formulas here, but I don't want you to look at like, oh no, we have to memorize a whole bunch of formulas. You don't. Okay. There's one thing you do have to memorize in this section, but for the most part, I try to keep the memorization of stuff down. So z-score is, okay, it's x minus mu divided by sigma. Remember, this guy is pronounced mu. This is the average. This is the population mean. This is an average. It's the same average you've been doing your whole life. You add everything up and then divide it by the number of things you added up. Okay. Remember this guy? This is called sigma. Okay, and this stands for the population standard deviation. Okay. If you're ever interested and you want this one instead, okay, X bar, remember this guy is called X bar. This is the sample average. And S, this is called the sample standard deviation. Technically, this would be called a t-score rather than a z-score, but people will say z-score for this one too. Okay, and nobody corrects them. It's a very subtle point. Okay, like exactly when should you be using a semicolon and when should you use a period? That's the difference. So here we are with z-scores. Right now, what a z-score is measuring for us is the number of standard deviations away from the mean. Okay, so what this is doing for us, it's taking a whole bunch of different values and it's just converting them into how far away is it from the average. Okay, and it's a really important way to think in statistics. Like in standard deviations, how far is it away from the center? Okay, and what we most of the time you're dealing with, you know, these bell-shaped. This is the average. Okay, these bell-shaped curves. Okay, because a lot of things happen to be, not everything, but a lot of things. Okay, this is what standard deviation away. Right. So most of the time we're looking at shapes that look like this, and we want to put in our heads and say, well, the further away from the average it is, the less likely that's going to be, right? So with heights, I know for human males, right, average height is 5'9". That happens to be my height. It's, you know, and I don't remember the standard deviation, but the further away you're going to get, the less likely you're going to see that, okay? So if I just add 3 inches, right, that's 6 foot tall. Okay, so like how many people do you know that happen to be 6 feet? Like, you know, it's not uncommon, but it's not like everybody's not, you know, every guy you meet is not 6 foot tall. How many guys do you meet that are 6'3"? Not that, or 6'6". I mean, if you happen to play on like a volleyball team or basketball team, yeah, you're gonna know more of these people. But in the general population, you're just not going to see them. And conversely, like how many guys do you know that are 5'6"? How many guys do you know that are 5'3"? Not too many. But I'm just going 3 inches away, 3 inches away. Okay, so the further away I get from the mean, the fewer people we're going to have. Again, if you work as a jockey, you probably know a lot of people, okay, that are 5'3", or a lot of men that are 5'3". Okay. 5'3" for a woman, I don't think is as uncommon as for a man. So that's generally the idea. Like when somebody says, you know, well, we measured this, I'm like, wow, that's really big. I'm like, relative to the mean, relative to the center, like how far away is it exactly? Okay, and that's what the z-score will tell us. The other nice thing about z-score is that x, whatever unit we happen to be in. So if I'm measuring heights, x would be in inches. The average would be in inches. The standard deviation would be in inches. So if I say x minus mu, right, this, we're going to add this up. That's going to be in inches, divided by the standard deviation, which is going to be in inches. That means we can cancel them. Okay, z is a unitless value. Okay, I don't know how many people that I have in the class that are going to be engineers, and you know, you might be. I mean, a lot of people, a lot of different kinds of people take this class. Engineers really love unitless numbers because they're really just factors now. Okay, it lets you compare very different things without having to worry about what units they're in. If you're an employee of the University of Phoenix, I apologize to begin with because I'm going to pick on them. If you had a very good experience at University of Phoenix, this is not meant to diminish your experience, but I do not have a high opinion of University of Phoenix. Okay. Say, for example, you're at our college and you scored an 80% on your stats test. Okay. And we have a standard deviation, or 80 out of 100. And then our standard deviation, so here's your score, X. Okay. The average score in the class was 70. Okay, this was their average. Okay. And our standard deviation is 10. Okay, it's almost always higher, but that I always shoot for that as a standard deviation. I think that's a good one. Right? And you have University of Phoenix student. I know how they teach there, and their average was a 97. Okay. Or you got it. No, let's make you a 90. Okay, this person got a 90 on their exam at University of Phoenix. That's X. The average there, okay, their average there, let's call it a 96. Okay, that's their average. And we'll make 2 equal to the standard deviation. I'm sure that that's higher. Okay. Who did better relative to the rest of the class? Okay, I mean, clearly this person's going to say, well, I got a 90. I did better than your 80. I got an A. Here's a hint. Everybody at University of Phoenix gets an A. Right? This is why most people don't take this class, take this school seriously. So what we're going to do, right, is we're going to calculate this. We're going to get x minus mu divided by sigma for both of them. Okay, so we have 80 minus 70. That's x minus mu divided by 10. Be very careful with your order of operations. You want to make sure that you're saying 80 minus 70 is 10 divided by 10, which is 1. Okay. Now, for the other side, for the University of Phoenix here, we're going to have 90 minus 96 over 2. So 90 minus 96, that's negative 6 divided by 2. That's going to be negative 3. So relative to the class, okay, your z-score for this is 1. You did 1 standard deviation above the average, whereas the University of Phoenix student had done 3 standard deviations below the average. Okay. Now remember, the further away you get from the average, the more likely it is. 3 is a big number for a z-score. Okay. Usually your answers are going to be between 2 and negative 2. Okay. Most of them are going to be between 1 and negative 1. But if you end up with a negative 3, like that's far enough away to say, well, that's an unusual observation. Okay, something weird happened here. Did you not see the last page of the exam? Did you get sick halfway through? What happened? Okay, that's what I want to know. So relative to the other people in their exam, like, you know, the relative to the difficulty of the exam, this student did so much better than this one. If there's 1 standard deviation above, that should be a B. 3 standard deviations below, technically this should be an F. Okay, that should be like a low F. All right. That happens, by the way, in medical school too. If you take a class and you're in a class with a bunch of people that are just really, really good, like they curve. And when I say curve, I mean they do this curve. So if you were in a law school and the average was 96, standard deviation 2. So, yeah, I got a 90, I got an A. But no, you fail. Okay, you are 3 standard deviations under the mean. That is a failing grade. Okay, so when you go to law school, pick good study partners. Actually, I'll tell you guys a story about that. My high school physics teacher graded like this. Okay, there'll be 1A, there'll be 2 B's, there'll be a lot of C's, there'll be 2 D's, and there'll be 1 F. Okay, which is kind of nice. Right? Only one person is going to fail this class, but well, there's 2 A's, 2 F's. Me and this other girl, and I have no idea. Okay, I was a disaster in high school math, and that physics teacher gave us multiple choice tests, and I just happened to have good physical intuition. I have no idea how I ended up with an A. No idea at mid-semester. And my friend was like, wow, you're really good at this. Trust me, I'm really not. But we decided we were going to cheat because he was like, I need to raise my grade. So here's what this thing sets up. So I helped him. Okay, don't cheat. All right. But what I did was we came up with, like, if you ever watch a third base coach, all the little sign language they do to, like, tell people, but because they're under observation. So, like, all you had to do is query. You had to say which number are you on, and then is the answer A, B, C, D, or E. So we came up with this system of being able to say, like, I'm on 27. What's the answer? And I would answer A, and like, would you touch your ear or touch your elbow, something like that. So we get these kids that are like, I'm sure the teacher knew, because we'd be sitting there fidgeting, right? But the thing is like, I didn't want to share my A with him because the girl sat up in the corner. She's really smart. Like, I'm not going to compete with her and you at the same time. Like, I'll push you down the stairs first. So about every 4th problem or so, I give them the wrong answer. Okay, Jason, I'm sorry if you ever see this video. Okay, but you still passed physics. All right. But yeah, I would sabotage them because here. So if you end up going to law school, you end up going to med school, and you were around people that are that mercenary, I'm not anymore. But if you're around people who are that mercenary about their grades, be very careful about who you pick for study partners. Okay. Most of my undergraduate career, all of my graduate career, we're helping each other out. I mean, we're not cheating, but if there's I think we have a lot of take-home tests, and somebody would be stuck. I'm like, I'm looking for this theorem, I can't get it. And like, you might want to look somewhere between the pages like 30, 34, somewhere in there. That might help you. So that's the cheating we did, was to give somebody, like, here's the part of the book you want to look for that'll give you a big key to, like, help you break this problem. But most of the other stuff, I mean, it was a very collaborative effect. So we didn't do any of this in grad school. So if anybody went to grad school with me, you can rest assured I did not purpose to sabotage you. I was still a disaster, but all right. Sorry about that tangent. So that's Z-score. And the reason why I want to tell you about Z-score, sorry for the length, is we want to talk about empirical rule. This is something you do have to memorize. Okay. Now, this only applies to symmetric, bell-shaped distributions. Okay, you're probably the same as I am, maybe even less with this. Like, I didn't live in the 18th century, so bell-shaped is not, like, that's not a thing for me. But I do make cookies at Christmas time. So the kind of bell we're talking about is like the Christmas cookie cutout things for bells. That's what you want to think about. Okay. So the people that came up with this, bells were very important. I don't know why, but they were. Okay. They keep time, I know. But Christmas cookies is like my only experience with bells like this. But that's what we're talking about. Okay. So if we have a distribution that looks like your phone, something like that, we are not applying the empirical rule to this. Okay. If we have a curve that looks like this, okay, bathtub curve, by the way. very common in lifespans. We are not applying the empirical rule to this. Okay, we are applying different rules. So here is empirical rule. We're going to assume a bell-shaped curve when we're talking about this. So we want 68%, we're going to know that 68% of the data, of the observations, is within one standard deviation of the mean. Okay, this is listed in your book too, so you don't have to deal with my crummy handwriting. 95% of your data is within 2 standard deviations of the mean. And 99.7% of your data, so it's not linear, of data is within 3 standard deviations of the mean. Okay. So what we're saying is like the further away you are, like the less likely it's going to be. Okay, or the group of things that are centered around the mean is most of your data, and there's very little that's outside of it. Okay, so if I look at 2 standard deviations within the mean, like there's only 5% that's outside of that interval. Okay, for 3 standard deviations of the mean, it's like there's only 0.3% that is outside of that interval. So when people tell me stuff, numbers in it, it's like I'm kind of applying this rule when I'm doing my, I mean, it's possible that this could happen, but it's not, you know, the further and further, you know, the more outlandish the story, the less likely I am to believe it now, because I know like most of the things are going to happen within here. So if you tell me something that's like, oh, it was like 4 standard deviations out, like you're going to have to bring something, okay? Like I'm sorry, I'm going to be skeptical of any claim that you make without a little bit of proof going on. Okay, so that's the idea: is the further away from the average, the further away from the middle, the less likely I think that you're telling the truth. Like, I caught a fish this big. Like, really? Okay, I'm not going to stop somebody from telling their fish story. That's fine. You can have that delusion, whatever. It's not going to hurt anybody. But unless you have it on your wall, right? I'm not believing you. Okay, I'm not going to challenge you, you know, at a party or something. But at the same time, I'm going to be a little skeptical. Unfortunately, I wear that on my face, and people can tell. But all right, how are we using this? Like, how does empirical rule and z-scores function at the same time? All right. So, oh, this is the same problem we did last night. Say in a recent survey, 655 working Americans, this is clearly before COVID times, the average weekly amount spent on lunch was $43 with a standard deviation of 272. I'm going to tell you that the one of the book has a cents thing here too, so it's a little bit harder to tell. Okay, and we want to estimate the percentage between these 2 values. Okay, now I'm not really good enough to like be able to just look at this number and know like, well, this is 2 standard deviations under the mean. Like, I can't tell. Okay, so since I have to compare to this table here, we're going to figure out like, well, how far away is 3484 from the average? Okay, so what is the z-score for 3484? Right, so we're going to take 30, well, x minus mu divided by sigma, right? So we have 3484 minus 43 divided by, what was their standard deviation again? Their standard deviation was 272. Okay, so divided by 272, right? So what we're going to do, okay, is we're going to go here. We're going to say, great, this is 3484 minus 43 equals, okay, so this was 816. Okay, and that is equal to, divide 272, 2.72, enter. Oh, look at that, -3. Okay, now those first couple of problems, and this, I'll check the homework for us. They might be in the book, there are some that are not automatically the other side. So this one's probably going to be 3, but you're not guaranteed that that's going to be the case. All right. I just want you to realize that you do have to check both sides. All right. And this problem 7, you thought you don't, but when they get a little bit harder, you got to check both sides. So 5116. So we're going to say z-score for 5116 minus 43. That's terrible. Sorry. 5116. Okay. 5116 minus 43 divided by 2.72. And this is equal to 5116 minus 43 equals, how about that, 816? 272. My suspicions were correct. Just be careful and double check these. They're not always going to be like the positive and negative number. So what percentage is within 3 and -3 standard deviations of the mean? So it's 99.7%. Right? That's how we do this. Okay, so I know this is we'll say almost all. That's another answer your book likes. And they're just going to take us one by one as we get here, right? Then we go on to a slightly, I'm going to see if I can't find another harder problem. All right, this is what I'm talking about. So we are going to go through and slice this up a little bit. All right, that's what we're going to do. This will be the last one, so we'll make it smaller. So 49, 39. Do we have the same scenario? Nope. So they randomize it, so that's good. So they changed it a little bit. So be careful. Watch for that. Average 4505. So my average is 45.05. Standard deviation, what is that? Standard deviation is 278. All right. And we want to know what? We want to know what percentage is less than 39.49. All right. What's the z-score for 39.49? Because these numbers are hard to look at, right? So we're going to say z is equal to 39.49 minus 45.05. Remember, this is x. That's the one. The x is always like the part A, B, and C. Okay. Mu they give you at the beginning. Standard deviation they give you at the beginning. Okay. So divided by 2.78. Okay. So let's go ahead and figure that out. Okay. So we have 39.49 minus 45.0, not point, it's 0.05. All right. And then divided by 278. So this is negative 5.56 over 2.78. By the way, the other thing about this is in this chapter, they should all come out to be plus or minus 1, plus or minus 2, plus or minus 3. 2.78. That is not true. We get to this in chapter 7. That's not true. Because we will come back to this. All right. So we have -2 here. How much of this stuff is between -2 and +2? How many of the launches were between -2 and +2? Well, that's 95%, right? So this shaded part in here, that's 95%. So if I say, well, I've got $1, 95 cents of it I've accounted for. It's in my hand. So I've got 2 more pockets to check. And I know that this last little bit has to be equally divided into these 2 pockets. Okay. I know it's not possible to split a nickel, but we're going to have 5% left over. 2.5 of that 5 is in one pocket, 2.5% is in the other pocket. All right. and they wanted to know how many people spent less than this. Okay, so that's going to be this value here. So we want 2.5%. That is the value, right? That's the percentage that we have that is less than that amount spent. That's the 39.49. Okay, so we're going to say 2.5%. Okay, so that's how we're going to do that. I'm going to stop here because it's been long enough. I'll try to put another one of these up tomorrow and we'll see how we're going to go. All right. So, right. So thank you for coming and we'll see you next time.